Have you ever wondered about the actual physics behind something as simple as catching a ball? Why a fastball stings your hand so much, but a little change in how you catch it makes all the difference? Well, today we're going to unpack exactly that.
All right, so let's jump right in with a puzzle that I guarantee you've already experienced firsthand, even if you never really stopped to think about the science of it all. It really does start with just a simple catch.
So picture this. You've got a baseball and a ping pong ball, and they're both coming at you at the exact same speed. Now your gut tells you, instantly, that catching the baseball is going to hurt a whole lot more, right? But why? If they're moving at the same speed, what's really going on? What's the big difference?
And yeah, this chart really lays it all out, doesn't it? The velocities are totally the same, but the mass? They're not even in the same ballpark. And that huge difference in mass seems to be directly tied to what we're calling the ouch factor. So, somehow, an object's mass is a huge piece of this puzzle.
Okay, so here's part 2 of the mystery. Think about how you actually catch a fast-moving ball. You don't just stick your hand out like a wall, right? No way. You instinctively pull your hand back as the ball makes contact. We all do it. We know it reduces the sting. But what is physically happening in that split second? Why does that little movement save our hand?
To answer both of those questions, it turns out the clue we need is kind of hidden in plain sight, right inside one of the most famous equations in all of physics, Newton's second law. We just need to look at it from a slightly different angle.
Okay, so we all remember this from school, right? Force equals mass times acceleration. But what is acceleration? It's just a change in velocity over a change in time. So let's just swap that into the equation. Now, here's where it gets really interesting. We can actually take that m for mass and tuck it right inside the change symbol.
And right about now, you might be thinking exactly this. Like, hold on a second. You can't just move letters around in an equation whenever you want. It feels like we're breaking some kind of math rule, but I promise it's totally legit. And here's why. It works for a really simple reason. The mass of the baseball isn't changing. It's not getting heavier or lighter as it's flying towards you. So since that m is just a constant number, saying the change in mass times velocity is really just another way of saying mass times the change in velocity. See? Mathematically, it's the exact same thing.
And just by doing that one little bit of rearranging, we've actually uncovered something incredibly important. This new combination of variables, this mass times velocity thing, it's so fundamental to how the universe works that it gets its own special name. This is our aha moment.
And that special name is momentum. We usually write it out with a lowercase p. The best way to think about it is as an object's mass in motion. It's basically a measure of how much oomph an object has, how much stuff is moving, and how fast it's going. The formula is as simple as it gets: mass times velocity. So a few key things to remember about momentum. First, because velocity has a direction, momentum does too. It's what we call a vector. Second, its unit is kind of clunky, kilogram meters per second. And most importantly, momentum depends equally on both mass and velocity. You change either one, you change the momentum.
This table just nails the concept. The baseball has a lot of mass and a lot of velocity, so its momentum is through the roof. The ping pong ball has the same high velocity, but almost no mass, so its momentum is tiny. Now here's the wild part. Look at that massive train. Because it's at rest, its velocity is 0. And anything times 0 is 0. That means the train has 0 momentum. A tiny, fast-moving ping pong ball has more momentum than a stationary freight train.
Okay, we've got our brand new tool, momentum. So now let's circle all the way back to the beginning and see how it just completely solves our baseball mystery.
And this, right here, is the big reveal. By rewriting that old equation, we've found a new, powerful way to think about force. Force is the rate of change in momentum. In other words, the force you feel is all about how quickly you try to change an object's momentum. A massive force means you're changing its momentum in a very, very short amount of time. So let's apply that to our catch. Your job is to take the ball's momentum and bring it all the way down to 0. Well, since the baseball started with way more momentum, stopping it requires a much bigger change in momentum. And if you make that big change happen in a split second, your hand has to apply a massive force. That huge force is what you feel as a sting. Ouch.
But that brings us to the final, brilliant piece of the puzzle, the time. Look at that delta t on the bottom of the fraction. That's the time of impact. And here's the thing. unlike the ball's mass or its initial speed, this is the one variable that you can actually control.
And this just lays it out perfectly. Look, in both cases, a hard catch or a soft catch, the total change in the ball's momentum is exactly the same. It has to go from moving fast to zero. But by pulling your hand back, you are deliberately stretching out the time of impact. You make that denominator, that delta t, much larger. And when you divide the same number by a much bigger number, the result is a much, much smaller force. And that feels a whole lot better. That's the art of the catch.
So what's the big takeaway here? Thinking about the world in terms of momentum isn't just a different way to do the math, it's a whole new and, honestly, more powerful way to see and understand how forces actually work.
This is it, right here. The force you feel or the force you apply, it all comes down to how fast an object's momentum is changing. If you want to reduce the force, you just have to make the change happen more slowly. It's the exact same principle that makes airbags work in cars or why gymnasts use padded floors. It's all about increasing the time to decrease the force.
And that leaves us with one last, really fascinating question to think about. We've established that you need an outside force to change momentum. So, what happens to the total momentum of a system if there are no outside forces acting on it at all? Well, that, my friends, is a story for another time. Thanks so much for joining me.